6 spheres of radius 1 are positioned so that their centers are at the vertices of a regular hexagon of side length 2. The 6 spheres are internally tangent to a larger sphere whose center is the center of the hexagon. An 8th sphere, which would be this one, as I will discuss, is externally tangent to the 6 smaller spheres and internally tangent to the larger sphere. What is the radius of this 8th sphere? Now, how do we approach this sort of problem? Well, first, it's a 3D problem. So the first step in any 3D problem is to convert it to a 2D problem. And that way we can use all our theorems that we are actually familiar with. So this would be a cross-section from the top view. We basically take a cross-section through the equators of these little spheres. And if you can imagine, we've omitted the larger 8th sphere because it will not show up in this particular cross-section. Now, upon doing this cross-section, we learn one very important fact. Now, we want to find the radius of the larger sphere, call it r sub l. And it turns out that this is 3, as we can see from this cross-section, and this diagram makes it instantly clear that it is the case. And the way to see that is that this makes a parallelogram, actually a rhombus in particular, with side length 2, making this side length 2. Or you could note that in a hexagon, it's divided into 6 equilateral triangles, which would make this 2, since we're given the hexagon has a side length of 2. So the larger radius is 3. Now, on to the next part. We take another cross-section, and if that could be thought of as the top view, this is this sort of, you could say, a side view. And this cross-section is perpendicular to the previous cross-section. And if you can visualize, it's through the prime meridian of the top 8th sphere. Now, how do we approach this? This is similar. We convert to a 2D problem, and now we notice that we have a very convenient right triangle. And we can just apply the Pythagorean theorem to find the radius OX, sorry, not OX, but this length, which is the radius of the 8th sphere that we desire. Now, call this r. Then we know that since the radius of the large sphere is 3, this is 3 minus r. And similarly, this is 1 that we're given. And since the radius of the large sphere is 3, this is 2. And this would be r, and this would be 1. So this whole side is r plus 1. R plus 1. Now we can just apply the Pythagorean theorem on this and solve the resultant equation, which is fairly straightforward. So we get 8r is equal to 12, implying r is 3/2, which would be b.